Our other algebraic strategy for solving a system of equations is called elimination. You may see this process referred to as solving a system by addition or subtraction in other textbooks and online. I prefer to call it elimination because I think it drives home the fact of what you're actually doing a little bit more than addition or subtraction as a name. When you will use elimination to solve a system, you are doing exactly what the name suggests. You are attempting to eliminate one of the variables. Yes, you're going to eliminate that variable through addition or subtraction, but the goal is to get us down to a one-step, one-variable equation. If we look at these two equations, you'll notice that they are in standard form. Elimination tends to work as a strategy really well if the two linear equations are in standard form. If they are not in standard form, you can still do elimination. It's just a little bit tougher to keep everything organized. So elimination works like this. We want one of those variables to no longer be there. We don't care which one, we just want one of them to go. And we do that by adding. If I just added this side of the equation, these sides of the equation together, and these sides of the equation together, I would get 26 on the right and 10x plus 1y on the left. That's not going to help me. I'm allowed to do that because of the whole concept of equals, and the fact that the left side and the right side of both of the equations are equal, and we're looking for the place where they intersect so that we want them to be equal to each other. Like, there's a lot happening in here that allows me to add the left-hand side and the right-hand sides together to create a new equation. But as it stands right now, just adding them like this isn't going to help me. So how do we get around that? Well, if we're looking at the equations, we notice that the 5y is positive and the 4y is negative. When we add it down just in that hypothetical scenario, we got really close. 5y plus negative 4y is 1y. What we want to have happen is for that variable to go away. In order to make that happen, we have to multiply both of these equations by some constant. Why are we allowed to do that? Well, because of the rules of equality. I can multiply these equations by anything I want and create an equivalent equation. I can multiply the top one by 64 and the bottom one by 32. And I would create equivalent equations. Equations that would have the same solutions, equations that would have the same graphs, two equations that would have the same intersection point. So I get around that by choosing the right number to multiply both equations by. And in this case, the right number to multiply the top equation by is 4, and the right number to multiply the bottom equation by is 5. The reason that we choose 4 and 5 is because that creates a new top equation of 16x plus 20y is equal to 60. Everybody got multiplied by 4. The 4 became 16, the 5 became 20, and the 15 became 60. The bottom one we multiplied by 5, 30x minus 20y equals 55. And I hope that you already see the reason why we would want to do it this way. The reason we want to do it this way is because now we have the 20y and the negative 20y. And when we add the two of them together, we're going to end up with nothing left in terms of a y. So let's add these two sides together. 16 and 30 makes 46x. 20 and 20 as opposites make nothing. 60 and 15 is 115. Or sorry, 60 and 55 is 115. We divide by 46 on both sides, and we end up with x is equal to 2.5. That's going to be the x coordinate of our solution. At this point, you're doing the exact same thing that we did with substitution. You're back substituting that number into either one of those equations and determining a value for y. I'm going to choose the top equation because 4 times 2.5 is a little bit easier to deal with than 6 times 2.5. Not that much easier, but I at least know what 4 times 2.5 is without really having to think about it. Plus 5y is 15. Notice I did not use the big beefed up version of the equations. I could, because it is equivalent, but I didn't. I can use this one with the smaller numbers in it. 4 times 2.5 is 10, plus 5y is 15. Subtract the 10, divide, and you get y is equal to 1. So our entire solution is 2.5, 1. We know that 2.5, 1 is going to work in the first one, so that one's good. If we check it in the bottom one, 6 times 2.5 minus 4 times 1. 6 times 2.5 is 15. 4 times 1 is 4. And you get 11, and it checks out. So as a strategy, elimination works in a little bit more specific situations. We like it in being in standard form. We're okay if we have to multiply both of the equations. We want to set it up so that we can add. But for elimination, we're going to multiply one or more of the equations by some non-zero constant. We don't want to multiply by 0. That's just going to create zeros equals zeros, which isn't going to help me at all. The goal is to have 2 of the coefficients be opposites of one another. And obviously, we want that to be the same variable. I wouldn't want the coefficient of this x to end up as the opposite of the coefficient of that y, like it is in that example. That didn't help me. That wasn't going to eliminate any of the variables. So I need those coefficients that are opposites to be attached to the same variable. We add the equations, eliminating the variable with the opposite coefficients. We solve the leftover equation, which if done correctly, this should end up being a one-step equation. If you start in standard form and you eliminate one of the variables, you should be left with a simple one-step equation, and then you back substitute and check your answer, just like we did for substitution.